Hello everybody. In this presentation I'm gonna discuss the research paper have been written by me, Zach and Chase. The topic I'm gonna talk about in this presentation is machine learning to predict new thermoelectric materials. We choose this topic because the whole world now facing some problems such as global warming and climate change, and the whole world need a new or alternate energy that could serve or help the need of the modern society. So we choose this topic to serve or help that need. In this presentation, basically, I'm gonna throw introduction, experimental methods, design of experiment, preliminary results, and after that, I'm gonna end with brief conclusion. So for the introduction, first of all, let's stop and talk what is thermoelectric material. Thermoelectric material is basically a material that could convert heat into electric energy by using a phenomena called Seebeck effect. As shown in this picture here, a Seebeck effect is basically needs two semiconductors. One of them is negative charge and called N-type. The other one is positive charge and called P-type. And these semiconductors should have heat gradient, and this heat gradient will help the electrons to move from the negative side to the positive side, which will create a current around this material. Worth to mention that the type of the semiconductors will change the properties depending on the valence electrons each semiconductors can carry and can release. So with that information, let's move now and talk about the experimental methods. So to reach our predicted thermoelectric materials, we gonna focus on two main criteria. The first criteria is composition-based feature vectors, which is known as CBFV. This criteria basically depending on the fact that the unit structure of each atoms or of each compound is affecting the properties of each compound, especially when it's combined with another atom. So by using the machine learning in this criteria, we're gonna use the CBFV as input, and we get predicted lattice as output. Using this computer machine will help us to eliminate and examine a lot of materials with faster rate than normal. The other criteria we're gonna focus on finding on the way of our finding of the new thermoelectric materials is basically using neural network machine learning, which known as NNML. Conjunction with the CBFV, the cubic structure could be incorrupted, and for that incorrupted, can we have or consider the nodes as atoms and each as bonds. And after applying a lot of irritation, we expected a new machine learning will be learned to specify the type of the thermoelectromaterials we need, and to specify the most perfect or optimal Seebeck coefficients. And this kind of study of the NNML, it's called or lead us to the deep learning. So the design of experiment. So our design in this experiment, we mainly focus in one goal is by using the web-based machine learning engines to predict a new thermoelectric materials that not traditionally regarded as a thermoelectric materials. We're gonna focus basically in elements in periodic table in 3 or 4 group, and we're gonna basic in elements such as titanium and SC. And we're gonna do too many rotations and machine learning in these basic elements until we're gonna flow deeper until we're gonna find a soluble material that be a better as a thermoelectric material. For our like first results we still in our beginning steps for this experiment. We use the first machine learning and it is run completely successful. In this machine learning, like in briefly, we use Casual kernel as virtual environment, and this machine learning help us to analyze the Seebeck coefficients and also help us to import some of the materials that Dr. Sparks gave us. In conclusion, we still, as I said in the beginning, we're still in our like first experiment. We need more time to reach something hopefully will be great, and we need to irritate more data sets such as valence electrons, and we need also implement more deep learning until like the model will identify its optimal elements by itself. Finally, I have to mention that our success in this project is basically, or most important, depending on only one thing, is depending on the ability of the neural network to predict Seebeck coefficients by mass fraction. That's all. Thank you for listening, and this is our references if you want to look them up. Thank you so much.